Welcome back. This is the second day of notes for the second part of our energy unit. And in this chapter, we talked last time about conservative forces and potential energy, so this time we will be talking about non-conservative forces. We're going to be dealing with energy that is lost in different examples, and it's lost in all sorts of fun little ways. So sit back and enjoy this. When we're talking about non-conservative forces, again, we're generally talking about energy being lost in some sort of situation. And usually when it's lost due to friction. It is converted to heat via friction. Whenever we're talking about an energy gain, usually we're talking about something where you're applying some force to a system, usually through a push, sometimes through a pull, but it's a scenario where you're giving energy to the system. And we have to make sure we take both of those two things into account when we deal with our energy equations now. So there's really two ways to describe what I just talked about. One way is just by saying this. Your change in energy is going to be equal to the work that is added to the system, and I put the A there for like an applied force is usually the way it's added to the system. You're applying a force on something, subtracted from the work taken away, usually due to friction. So that's typically what we're looking at here, and this is one way to describe that equation. So if you wanted to examine this a little bit further, change in energy, of course, is going to be equal to the addition of all your final energy minus the addition of all your original energy. And then that's going to be set equal to applied work, which would be applied force times displacement minus the energy lost, the work that's taken energy out of the system, force of friction times displacement. So that would be your long equation there, and that's what we'd be dealing with. The other way of writing this, and the way that I probably prefer, because it kind of tells a story, is simply this. You start with a certain amount of energy. Maybe you add some energy to that system due to an applied force, and then maybe you take some energy out because of friction, and whatever you're left with is your final energy. So like I said, it kind of tells a story from beginning to end. You start with some sort of energy. You either add some or you take some away, and then you're left with whatever you have left over there. And I'll just describe this one more fully like I did up top too. And of course, this will get longer when you further describe your potential and kinetic energy in their own specific equations. In general, what this is all saying is that your overall change in energy is equal to the net work from the system, where your net work is equal to the work added to or subtracted from that particular system. It's added via an applied force usually, and it's taken out via friction. Those are both non-conservative forces. One other thing to just take a quick note of here is gravity is a conservative force, as I mentioned in the previous video. And so because gravity is a conservative force, it's not going to play a part in work being added to or subtracted from this system. It's a conservative force, therefore we're not using that in these equations. Gravity is taken into account when you're talking about potential energy. So just wanted to make a quick note of that. All right, I'm going to go through a couple examples here. Here is the first. Take a minute, let that sink in. So we've got our object on the top of this incline, and we know a whole lot about it, which is a nice change from, from what we usually are given here. So we know that it's a 30-degree angle. It's going to travel 1 meter down the incline. Force of friction is a constant 5 newtons. You can see it is a certain height from the bottom of the incline there, described as y original. And you can find that original height just by using a sine relationship. Sine is equal to opposite over hypotenuse, and your hypotenuse is 1. You have your angle of 30 degrees. This is the opposite side. So when you do that, you can actually solve directly for that height, and you get 0.5 meters for it. Now the question here is going to be, what is the velocity that this mass has when it reaches the very bottom of this ramp? And that's what we're going to go ahead and try and solve for in this, our first example. Alright, so we're going to be using energy, obviously, to try and figure this out. And what I'm going to do is I'm going to solve it the way I like to solve it, with that second equation that I described in a minute or two ago there. So let's just start from the beginning, work our way through, and hopefully we're left with just one unknown in that equation. In the beginning, we've got original energy, and maybe there's some energy added to the system through work. Maybe there's some energy taken away due to friction. And in the end, we're left with something when it reaches the bottom there. This is our general expression for the way that I like to approach these non-conservative force problems. So, let's be more specific here. What kind of energy is present at the beginning? Well, it is at rest on top of that incline. Because it is at rest, there is no kinetic energy. All we have for an original energy is potential. As far as an applied force, there is no applied force on this system. Yes, gravity is kind of, you can think of it as applying a force, pulling it down, but again, gravity is a conservative force, so it does not go here. Potential energy takes the effect of gravity into account. So there's no applied force there, and so there's no energy being added to the system, but there is energy taken away. And that energy being taken away is through the force of friction, and it's exerted over that entire displacement of 1 meter. And we set that equal to whatever energy is left over at the end. When it reaches the bottom, it is at the bottom, which means it has no potential energy. So all it's got on the bottom is kinetic. So let's go ahead and boil this down even further. Potential is mgy. All right, so there we go. If I want to solve for velocity, I'm just going to try and isolate it in this equation. I'm going to multiply both sides by 2 to get rid of this 1/2. And I'm going to divide both sides by m to get rid of that. So this is just going to turn into that. And of course, to get rid of the square, we erase it. And if we erase it, we got to square root both sides. So that's our expression. And we've got enough information to solve for a change. We don't have to do any other fancy work. So let's just put our numbers in here. Mass is 3 kilograms. G is 9.8. The height is 0.5. Force of friction is 5 newtons. And the distance is 1 meter. I think I got all the parentheses there. Then it's just a matter of plugging all that in. And when we calculate this out, I get 2.54 for that velocity. And that's how fast it's going at the bottom of the ramp. Something else I just want to make known to you is kind of a little shortcut through some of these problems. Whenever you're on an incline like this, and maybe you're not actually given the force of friction directly, maybe they'd want you to, do force diagrams to get normal force in order to figure it out. In general, the energy that you lose due to friction is simply going to be equal to mu mg x cosine whatever the angle is. So if you want to use this as a shortcut, I'm totally fine with that. If you want to go ahead and you do the force diagrams to figure it all out, you're welcome to. But, I mean, that's what it's going to be equal to, as long as you're given this angle. So yeah, enjoy that. Mu mg x cosine theta will be equal to the energy lost due to friction. Up next, we've got a fella going down a slide. So there he is. And he's going to find his way down this slide. And he'll reach the bottom. So here's the bottom right here. He is at an original height of YO, original Y. And we'll say for the beginning that there's no friction. And then we'll do a problem where there is friction. So, let's say I want to figure out the velocity that this guy has when he reaches the bottom of the slide. This is going to be pretty much a review from even stuff that we did last year in regular physics. straight up conservation of energy. There's no energy being lost in this case. So original energy equals final energy. At the beginning, he only has potential energy. At the end, he only has kinetic energy. So you can just set those two things equal to each other. M's get canceled. So to solve for that velocity then, multiply both sides by 2. And to get rid of the square, you got to square root both sides. So that would be your equation in order to solve for the velocity. And if his height was, we'll say this is equal to 2 meters, then you can actually plug 2 meters in here and come out with a number. When you do that, then you would get 6.26 meters per second. And that would be the velocity at the bottom of the ramp, assuming that there's no friction. Of course, usually, in most ramps and most hills, you've got friction there. So let's just take a look at an example where maybe we're trying to calculate how much energy is lost from the top of this hill to the bottom. All right, so if we want to calculate our lost energy, obviously friction is no longer going to be equal to 0. Let's say that, in the last example, we didn't need a mass because it canceled out. Let's just say that a mass is going to be equal to 20 kilograms. And, he was going at 6.26 meters per second at the bottom originally. Let's say that because of friction, he's not quite moving that fast when he reaches the bottom. Maybe his final velocity is 3 meters per second. If this is the case, how much energy has been lost? So to find that lost energy, you're just taking the energy difference. What is the energy at the end? Minus the energy at the beginning, and then you should be able to get your number. Energy, of course, is in units of joules, so that's what your units would be. And then we could just plug those numbers in directly. Whoops, I made a mistake. So, of course, originally he doesn't have kinetic energy. So, originally he's got potential energy. So, potential energy is mgy. And when you do that math and you plug it all into your calculator, you should get negative 302 joules, which just means that that's how much energy was lost from beginning to end. Of course, energy is a scalar, so we don't need to call it negative. 302 joules were lost in this scenario. Okay, I've got one more example for us here. This one's going to involve springs. This is kind of an interesting one. I did draw this one already. And truth be told, I'm pretty proud of how well it turned out. Sometimes my drawings are a bit shady. So you can... There we go. So just take a quick look at this, and I'd suggest copying this down right now. If you're watching it on a video, then you might want to pause it right here, get this copied down, because I'm going to be referring to this picture a lot through this problem, and I'm not going to be able to have it right in front as I'm going through. So, just to walk you through a little bit about what's happening. So here we've got this mass. It is moving to the right. And the mass is in blue. This green thing is a spring. So this mass is headed towards that spring. X equals 0, that's the equilibrium position. The spot at which this spring will just naturally be if nothing's pulling or pushing on it. Then here, in position B, you can see the mass has encountered the string and it's starting to bunch up. And down here in letter C, where the velocity is now equal to 0, this mass has fully compressed that spring to the point where it's not going to compress anymore. And letter D here, velocity D, that's just after the spring has pushed back and released the mass to the left. So I just want to walk through a little bit what's going on with the energies in these equations. So in terms of the energies here, on the top, as this mass is coming in, it only has one kind of energy, kinetic energy. So the energy at A is, again, A, B, C, D. The energy for scenario A here is all kinetic. 1/2 mv, and that v is the velocity in this position at A. The second scenario is the most complicated of the four. Here, not only is the mass still moving, but it's also compressing that spring. So we've got two kinds of energy going on here. We have kinetic energy, because the mass is moving, and we've got spring potential energy. And when you add those two together, you know, this is what those expressions turn out to be. For the next one, in letter C right here, as it is fully compressing that spring, now we're down to just one form of energy again. It's all spring potential energy. So the energy at C is all spring potential. And then the last one, now that the spring has effectively shot the mass back over to the left, now all of the energy is kinetic again, because the spring is completely unraveled. It's back to its original orientation there. So this is the scenario we're going to be looking at here. So let's first put some knowns on the board. We'll say that the mass is equal to 0.8 kilograms. We're going to say that the velocity at A is equal to 1.2 meters per second, and we'll also say that the spring constant K is equal to 50 newtons per meter. So that's what we know about this situation in terms of numbers. So one question might be, how far does that spring compress down here? How far is this spring from the equilibrium position that it was originally at up here? How far has it actually been pushed in? how far does that spring compress? In other words, we're going to try and solve for that x, the compression distance. So if I want to consider what's going on here, you know, the same energy is present for all four of these scenarios. It's just in different forms. Here it's all kinetic, here it's all kinetic, here it's all spring potential, here it's a combination of those two. So I'm going to be dealing with letter C here, the energy at C, because I need to figure out that compression distance. But if the energy is the same everywhere, I can set that energy equal to any of these. And because I know the velocity it has coming in, I'm going to set it equal to kinetic energy in this first part of the scenario here. Original energy equals final energy. So originally, it's all kinetic at A. And at the end, when it's fully compressed, it's all spring potential at C. So I'm just going to plug the equations in. Hopefully the numbers work themselves out, and we can finish. I'm going to go ahead and get rid of these 1/2 here. And in order to isolate my compression distance there, I got to divide both sides by K. So and then in order to get rid of the square, I can take the square root of both sides, and that would be my expression. So I can just plug those numbers in. Again, you can just toss them in. That's fine. If you're looking to be a little extra cute, this velocity is squared, so you could yank that out. And you'd have this expression. Whatever. So the mass, 0.8. So there you go. You go ahead and plug that into your calculator. Hopefully we get the same answer. I got 0.152. And that is the compression distance that this spring has undergone from beginning to end. So it's 0.152 meters away from where it would be if nothing was touching it. So there's an example with, just conservative forces. No energy is being gained or lost. Now, of course, let's use non-conservative forces. And this will be how we wrap up this video here. So now I want to solve for the exact same thing, but now we've got friction. And we'll see how this changes our answer. So, normally I'd want to solve this using that energy expression, original energy, plus work due to applied force minus work due to friction equals final energy. That's how I would personally approach this. But I want to make sure you see this in as many ways as possible. So maybe you preferred the other equation. Maybe you like this one a little bit better. And that's okay. So if we approach it this way, there's no applied force here. There's nothing acting on this mass or this spring. Aside from the mass in the spring, there's no external pushing force. So the applied force is 0. My change in energy, final minus original, is going to be just the energy at C minus the energy at A. I'm going to use the same two positions that I did before. And again, I could substitute that out and use the position at B instead of A, but that would be way more complicated because you've got two pieces of energy. So forget that. But if you want to give it a shot, you go right ahead. So that's our energy difference, and that's going to be equal to this energy that was lost due to friction. So let's go ahead and see where this takes us. So the energy at C is all spring potential energy. So 1/2 kx squared. At A, it is all kinetic. And of course, when we're talking about the work lost due to friction, that is equal to negative force of friction multiplied by the displacement, how far this friction has been acting. So that's where we're at right now. If we want to go anywhere with this, we've got all these numbers, except for the distance that we're looking for here. So in order to actually figure it out, I need to make sure I know what this number is here, my force of friction times distance. So I'm going to go ahead and do that here. So force of friction is mu mg. And mu is 0.5. The mass is 0.8. And of course, G is 9.8. And the distance is a number that we don't know yet. Might as well say this is that compression distance C, the same number that's over here. And if we multiply all of those numbers together, looks like it turns out to be 3.92. And now we've got an expression that might do us some good here. I'll kind of start up here now. So this guy over here, I'm going to put some numbers in. 1/2 times k, which is 50. We've got that compression distance squared. Then we've got minus 1/2 mv squared. And that original velocity is still 1.2. And that's going to be equal to negative 3.92, as I just calculated, force of friction here. So we got to make that negative now. Negative 3.92 times xc, if you can read that. I know that's a ways away. So, well, let's get this down into some nicer numbers here. 1/2 times 50 is 25. So we've got 25 x squared. This one, 1/2 times 0.8 times 1.2 squared, 0.576. And then over here, we've got 3.92. And what I'm going to do is I'm going to pull this 3.92 into the equation. And I'm going to put equals 0 on the other side. So because it was negative, it becomes positive when it gets to this side of the equation. What do we have here? That's right, we have ourselves a fancy old-fashioned quadratic equation. So, if we want to write this a little bit nicer, I suppose it would be 25x squared plus 3.92x minus 0.576 equals 0. 25 then would be your A, 3.92 would be your B, 0.576 would be your C. And if you plug that all into your quadratic equation, either the long way or the short way through an app or a calculator, you're going to get a grand total of a distance of 0.0924 meters. Whew. So there you go. As we would expect, this distance is much less than the original 0.152 meters. And of course, that's because some of that energy was lost due to friction. So those are non-conservative forces. And that's pretty much the bulk of this chapter. There's just a small portion that'll come next that will be on energy diagrams and stability and equilibrium. But this is the vast majority of this. And I know this looks like a lot, and when you're dealing with energy, there's a lot of equations here. You know, in the same way that in the force section, you could break it down every single time to just F equals ma. Your net force in whatever direction you're moving is equal to mass times acceleration. This also has an easy way of looking at it. Overall, the energy that you start with minus whatever energy is taken away due to friction plus whatever energy is added due to an applied force is equal to your final energy. And that's pretty much like your F equals ma equation from the last chapter. Everything that you're doing in this chapter kind of goes back to that. Energy is conserved if you don't have friction or applied forces. But if you do have to deal with those, that's how you do it. And I want to write that equation out just one more time. For those of you who have hung with me all the way to the end here, the equation that I like the most in this chapter is simply this. You begin with a certain amount of energy. Maybe you add some energy to the system from an applied force. Maybe you subtract some due to friction. And that'll just end up being equal to whatever energy is left over. That'll about do it for non-conservative forces. See you next time.